Now, as for my talk, I have 15 minutes, so it will be a bit of a rapid fire thing. If you have, so most of the concepts I will just touch very quickly, and then hopefully if you find them interesting, we can go deeper into it in the afternoon. So, oops, that was a bit too fast. So yeah, given the time constraints and that we're already a little late, I will just try to give you an impressionistic rapid-fire sketch of a complete interpretation of the theory of causal fermion systems. This is the conceptual ideas are all from a joint work with Patrick Fisher. I guess by now you all know him as well. Now, just a quick reminder for those who haven't been here on Monday, what is a causal fermion system? So it consists of these three structures. So we have a Hilbert space. We have this set curly F of bounded self-adjoint operators with n positive and n negative eigenvalues, which we should think of sort of all possible correlations, local correlations that can be realized in a physical system. And then we have a measure on top that picks out which correlations are actually realized in the particular system we're looking at. Now, I'm very happy that for once I don't have to give a full introduction of causal fermion systems, but one thing we did not mention on Monday, if I am not mistaken, is that we actually do have a causal structure on this curly F. Namely, the way it is defined is you look at the operator product on any 2 points, and then you look at the eigenvalues of this operator product, and this allows you to basically, we call the point space-like separated if all the absolute values of the eigenvalues are the same. What this implies important from the way the Lagrangian is formulated, there is space-like separated points do not contribute to the action. So for all practical purposes, we can ignore them. That is what I will use at some point. Then time-like separated and light-like are essentially the others. Details not so important. It's just important that we have them. Okay, sorry. Somehow it's delayed. Now, quick reminder of the inherent structures we have. So every space-time point comes with the attached spin space, namely the eigenspace of the local correlation operator. And so basically they are subspaces of the same Hilbert space. And we then have this structure of the physical wave function, which given a vector u in the Hilbert space, we just project onto the eigenspace of the point. So this is our u. So our psi u of y is the projection over here. Psi u of x is the projection over here. Okay, this is just sort of on the background. Now, first concept I want to introduce is that of subsystems. So causal fermion system is an ensemble of wave functions. So essentially think of it as an ensemble of fermionic particles. Now, what is a bit weird in comparison to sort of standard approaches, you have sort of in solid state theory, for example, you have the Fermi limit. So you have the states are filled up to some level, but then you have your Hilbert space is larger than that. But in causal fermion systems, sort of the whole Hilbert space is relevant. So now to make more contact, with the standard formulation, we embed our Hilbert space in auxiliary Hilbert space. And then we define sort of our state on this auxiliary Hilbert space as just basically the projection onto the physical Hilbert space, which is realized in which is the part of the causal fermion system. Now we can define sort of a subsystem then as a subspace of our physical Hilbert space, and together essentially with the projection onto that subspace. Now, if we take the entire physical Hilbert space and the state that projects the projection onto that is what we refer to as the total system. Important, we can also define one particle subsystems, meaning just projections onto one state in the physical Hilbert space. Now, an immediate sort of question then is, okay, what about Pauli's exclusion principle? And given the definition, it's a bit circular and trivial, but still just interesting observation. If we define sort of the occupation number of a state simply as the expectation value of a of our subsystem in the with respect to any vector sort of in our auxiliary Hilbert space, then what we get is that this expectation value for any state is always smaller or equal to 1. Now, this is just as a quick teaser. This is not technically anything substantial, but it's just nice, sort of given the Pauli exclusion principle and everything, we see that it's sort of baked into the violation of Pauli exclusion principle experiments. We see that it is baked into the thing here. Okay. Now, one thing that we were thinking about always is sort of, okay, well, what are observables in causal fermion systems? And Patrick and my approach were essentially, well, we only want to work with inherent structures to causal fermion system, and then there's not that much you have available. And sort of the definition of position observables is then given by this expression here. So essentially we say the position observable for the fermions for a space-time region U is simply given by the integral with respect to the projection onto the eigenspace of the projection operators to the eigenspaces with respect to our space-time measure rho. And the expectation value for any subsystem is then just calculated the way you would do in standard quantum mechanics. Now, one immediate property of these observables that makes them sort of suitable and nice is that they are always positive. So it's a positive chance of finding anything somewhere in space-time. And moreover, for any region in curly F that is outside of our space-time, the operator is 0. So we can only observe things in our space-time, which is kind of nice. Now, the further interesting aspect is if we look at the sort of the expectation value to find anything in a space-time region omega, a space-time region U, then this is just given, so that means the expectation value for the total system, then this is just given by the volume of this space-time region. So sort of the volume of the space-time region is kind of like the observation, the probability of observing any particle in this region. The battery seems to be a bit dead, so I have to stand over here. Now, the idea is we want to have some notion of space-time superposition or sort of subsystem spacetimes. And here we simply take the one particle or the subsystem measure, which is just defined as the measure that is given by the expectation value here. So we have here now, so we have the measure of the subsystem is it's just defined in this way. So that is saying if I have, let's say I have the physical wave function associated with a subsystem vanishes in some region, then this region is not part of my subsystem spacetime because the subsystem measure would disappear. So we get essentially, we can define a subsystem spacetime for any measure there is. And one thing we get is, again, sort of the sum of all the subsystem measures is the total measure. So we are consistent. And of course, the union of all our subsystem spacetimes is the spacetime itself. An important point here, if we have two of these subsystem spacetimes and their support is intersecting, so it's non-empty, and we have 2 points that are in this intersection, so they are both in M1 and M2, then the causal character So the causal relation between these 2 points is independent as to whether we regard them as elements in the subsystem spacetime of system 1 or of system 2. So so if you do the superposition of spacetime, sort of the causal character, so the character of the causal relation, not necessarily the causal distance, will always agree. God, I'm not going to learn it. Yeah, so now one last definition is that of a localization of a state. So basically here the idea is if we have our space-time M, we say that a state is sort of localized in a region, in this region, what do I call it there? U. So we say it's localized in U essentially when this region, if we remove it, it decomposes, like the subsystem space-time splits into a future part and a past part that are disconnected. We say a state is completely delocalized if the subsystem space-time agrees with the total space-time. And now, yeah, I'm not going to learn it. Now, the idea is that the fermionic projector gives us the 2-point, I explained this on Monday, this is basically a 2-point correlator. So for the action principle, we want to look at the 2-point correlation strength. And for the physical, for the theorem to work, we have to set this 2-point correlator just to 0 for the space-like separated ones. They don't contribute to the action anyway, so this is from the physical point of view, the space-like part is irrelevant, so we can do this. And then we define simply the 2-point correlation strength as the expectation value of this operator with respect to the subsystem. So this gives us kind of a, well, heuristically sort of a notion of distance, and the total 2-point correlation strength is then just the sum over all states. Now, if we formulate it like this, and we assume that the fermionic projector has a particular form, namely this scalar vector form, this is, among other things, satisfied in Minkowski space. So in somehow one case we care about, then one can show that actually this causal fermion system Lagrangian is equivalent to the variance of your causal correlation operator, or essentially of the uncertainty in your causal correlation operator. So basically, if we consider the correlation strength sort of to be a proxy for causal distance, then the causal action principle can be thought of as a principle of minimal fluctuations in your causal structure of the one-particle spacetimes with respect to the total system. Yeah, so now just a last thing. I want to give you a quick idea of how to describe experiments. So how do you test a system or a theory that comprises the entire universe from, and you want to test this theory or the system from within itself, right? We have no test particles or so. We have to do tests from within. And second, the question is, how does a purely relational theory give rise to sort of the conventional experience of time and space? And here, the idea is we take the total system and we split it into a probe and the background, with the probe having the dimensionality of the Hilbert space of the probe being much, much, much smaller than the background space. So this is, yeah. And then in the next step, we look for a macroscopic continuum limit description of our background space-time in terms of emergent variables such as the metric, the electromagnetic field, and so on and so forth, which we can identify sort of via the local correlation map. And then the idea is, if we do an experiment, we study the evolution of the probe with respect to the web of correlations of these background states. So this is essentially what we're doing. Now there's two caveats, of course. The first one is, of course, that I have now secretly assumed that the web of correlations spanned by the background system admits an approximate effective description as in terms of the continuum limit. And secondly, to be able to study the evolution of a system in a laboratory, we have to be able to meaningfully localize the probe on the scale of the experiment, right? If I cannot say, okay, my probe is now here and later there, I cannot do any experiments. Now, this is sort of the rapid fire conclusion. I took this picture yesterday at the Kepler Museum. Could there be a nothing? And the gist of everything I'm telling you here is that essentially, according to causal fermion system, there's nowhere where there is nothing, but there can be many places where nothing can be localized. So you don't have a localized state in a certain region, but the space-time, or like the web of correlation, still exists there. Yes. Okay. So I'm in time.